almost time.
Yeah, a couple of minutes. So what's the deal with the cameras?
They're live streaming the sessions
Okay, where?
on the internet.
Okay, open or
Yeah, yeah, yeah.
because I never signed anything to permit that.
Uh, is,
I don't mind, but usually there's like a whole thing about having you sign waivers.
um, yep, they are. Do you need me to get them to not?
No, no, it's fine.
Okay.
It's just I'm very surprised that you.
Yeah, that's a good point. I'm gonna actually go bring that up to Heather right now, actually. But that's a really good point that it probably should have been approved because I imagine that the Facebook people probably would have also wanted that done. And
Yeah, I mean maybe because it's in Europe, but usually like these types of things are
yeah,
more locked
yeah,
down
I
in
know. I
Europe
didn't.
than.
It didn't even occur. Like I know that. I mean, I've had to sign it a ton of times. So, but it just didn't even occur to me. But it's okay. You don't need me to.
No, fine, I'm fine. So
Okay, but
yeah,
I'm gonna go bring it up. So I'll let you know what I find out.
yeah.
Okay. I mean, you can just go ahead and start.
Okay, so I'm Úlfar Erlingsson. I run a security research group at Google. Before that, I was at Microsoft Research for a while. I've done a bunch of startup work and done a lot of language-based security since the mid-90s onwards. So this talk has a very buzzword compliant title, lots of buzzwords in there, but actually they are relevant and make sense of the context. Um, that said, there's a lot of content in the work. There's a paper for IEEE CSF that's about 6 pages that sort of contains the details. You can find it on archive if you look for data-driven software security. If you are missing something as you're following along, then just look for that. Uh, Now, I don't know how many people here actually work on computer security, but you all write software. And as such, you all interface with computer security in one way or the other. Uh, People quickly realized that the security of software artifacts and computing was a critical element. And as soon as there was multi-user computing in the 70s and in the early 80s, most of what we think of as the core abstractions and concepts of computer security as practiced today were already developed. Maybe some of the few things that weren't there already were things like firewalls. But the key concepts were there. Software protection and access control papers from the 60s and early 70s by Lampson and Salzer and Schroeder from the late 70s are sort of the seminal papers of outlining what is computer security and how does it relate to things that we craft. Now, unfortunately, those papers were describing concepts that needed to be applied and practiced to make secure computing systems, but somehow we don't have secure computing systems. In fact, you could argue that we have less secure systems now than we ever had before. And by most metrics that you would think of, sort of end-to-end metrics like how likely is a user of a computing system to be affected by a software security problem in a given year, we definitely are at one of the worst points that we ever have been, probably at the worst point. Certainly we are worse off than we were in the 70s and 80s when these principles were being defined. So what's up with that? Now, one of the people who sort of defined the field, Butler Lampson, gave a series of talks about 15 years ago and wrote a couple of papers trying to figure out, well, what is this thing, computer security, and what happens when it meets the real world? And one of the conclusions from those contemplations and retrospectives in those papers is that computer security might be imagined to be easier than real-world security, because after all, computers are very good at doing exactly what we tell them, so we just have to tell them exactly what to do and define that well, and they won't allow any bad things to happen. But in reality, this precision by which computers work actually works against us. And computer security turns out to be harder than real-world security. And that's because real-world security has a lot of built-in attributes that simplify the problem, such as the fact that somebody who wants to break a window, although a window is a very weak defense against burglary, has to be there right at the window in most cases. So there's this built-in assumption or Bayesian prior that you can only be attacked by people who are physically present. Whereas in software security, we really are dealing with the correctness of software, and any one problem can be attacked and utilized in an exploit as often as the attacker desires. The computer will do exactly the wrong thing in exactly the same way every single time, and the attacker can be present anywhere in the world. So this is a problem, but one of the really nice things in this line of work by Butler from 15 years ago, this is the same line of work where he defines what's called the gold standard of AUs, authentication, audit, and authorization, is that he describes how software security is actually not a different problem from what we usually think about when we think about software. It's just a form of correctness. And as O'Hearn was talking about this morning, programmers are not very keen on giving functional specifications for the programs that they write. It takes a lot of time, it's difficult, it's hard to maintain, etc. But at least programmers might know what a functional specification should look like. Now, in security, the specification is called a security policy, and it defines what should be allowed to happen. The problem is that nobody knows what the security policy looks like. It depends on how you're supposed to be using this code, who are the users, what is the purpose in using the code, etc. So the programmer is not the right person to be writing that in most cases. Now, just as we have for functional correctness, we have a specification and then we have an implementation that hopefully implements correctly that spec, and correctness is something we can check and strive for. We can use different methodologies to try to simplify establishing that correctness. In particular, we can use functional programming, which is one particular methodology, or we could use logic programming or various other programming methodologies that actually help establishing correctness. But, you know, we could also just establish correctness of machine code. It's just going to be harder. In security, it's the same thing. The implementation is called an enforcement mechanism. It takes this security policy that nobody knows how to write and makes sure that that actually is enforced correctly at runtime, or even beforehand. You can do static analysis and so on. And if we know for absolutely sure that there's nothing bad that can happen that will violate the security policy, we have assurance. And all of this happens, just as we have these different methodologies, all of these happens in a security model, a way of thinking about how we write down these security policies. And there are lots of different security models, just like there are lots of different programming methodologies. And this correspondence between methodology and security model is something that I added to what Butler defined in his papers. But no matter how you intend to define the security policy, no matter what model you like, it's basically really hard to get one. So it's much harder to get a security policy than it is to get a functional spec, and a functional spec is already very hard to get. We never get those. So the most successful, and again, security is a very dismal field, so things really have been getting progressively worse. But the most successful aspects of security is when we get the policy for free somehow. And one of the best ways of getting the policy for free is to get it from the programmer without having to get the programmer to write it down. So Mark Miller just sat down, so he likes a methodology where programmers write in a certain structured style using capabilities, and automatically, as they write the program that way, we should get some properties of the program when it runs, that actually will help with security. Most other developers like type systems. So we like to write things in a type-safe language, and we get guarantees that way. But even in an untyped language, we can actually get guarantees if we analyze the program, such as you can analyze JavaScript and actually figure out that certain things are true or not true based on static analysis. In C, one aspect that has actually been very successful is to take some of the implicit things that the programmer is excluding, such as the code should not be messing about with the return value that is stored on the stack. This is an implicit assumption that the programmer makes when writing the program, and why don't we just enforce that at runtime? So that's called stack guard. It's been baked into compilers for at least 15 years. It's ubiquitous. There are various other similar checks that actually are making undefined behavior in the C language be defined as a violation and halt. And so simply, if you take all of the things that are undefined, like, say, jumping into the middle of a function body or an expression evaluation, and disallow those, you actually improve security without having to get the programmer to write a new spec for these low-level languages. And this has been very successful. You can think of that as what we sort of have as a programmer intent security model. So let's just figure out what the programmer intended to happen as much as we can and have only that happen at runtime, and that's a form of software security. Now, in this talk, I'm going to propose a data-driven software security model, and since I work for Google, I like to use big data and imagine how we could actually figure out using big data to get the world into a better place. So why might we do a data-driven approach to software security? Well, remember that what we think of as computer security was really defined in the 60s to the late 60s to the early 80s. But the software we use today has absolutely nothing to do with the software that existed at that time. So if you have seen these orange juice makers that are popular in Europe, and you sometimes see them in the US as well, where you have this machine that takes oranges at the top and it rotates and it halves the oranges and it makes juice, and juice comes out the bottom. That's kind of what we think of as software. We have a sheet of Algol 60, or a sheet of algorithm, and that's our program, and we statically analyze or we reason about that program. That's software as traditionally imagined, certainly as imagined for these security concepts in the 60s to 80s. But in fact, what we have today is a lamp stack that implements an orange juice maker with an HTTP request, and you get orange coming out. So you can think of that as sort of a pentagon-sized building with libraries and other things somewhere inside of it, doing all kinds of things for who knows what purposes, but you know that there is a receptacle for oranges on one side, and there's a spigot that gives juice on the other. What happens inside, we don't really know. Now, we can think of that as software is really a found artifact. So it's a spaceship that came, and it seems to serve the purpose of making orange juice, and we just have to deal with it. Now, this seems a found artifact. You could use a data-driven approach to trying to reason about what is it and what should it be allowed to do, and what does it do. And it sort of nicely fits in with a bunch of other things where we have big, hard problems, and we use data like on spam fighting and so on. Now, in particular, I said that one of the things that wasn't sort of thought about in the 70s was firewalls. So firewalls are actually an essential part of modern computing, and they're kind of hidden. We forget that they are a huge success story. But imagine if we turned off all the firewalls on our machines and just let network packets flow. Well, we wouldn't immediately have worms and viruses, and basically the world would grind to a halt. And that's because the software is so bad So it's kind of like that Pentagon-sized building all of a sudden opening all of its windows and then letting anything come in. Well, bad things would happen. And by having those windows be closed and only having that one receptacle, we managed to greatly reduce what possibly could be happening inside that building, although we don't really know how much we have achieved. We've achieved something. So a data-driven approach might use historical evidence, what has happened in the past, as a way of trying to figure out what should happen in the future and trying to limit the attack surface, trying to see that, well, people tend to use this receptacle here for the oranges, and they tend to use this spigot here to get juice out. Collecting all of this historical evidence is one reason why previous attempts at something like this have really fallen into the case of intrusion detection, where you have some test software that you look at and you try to figure out, well, what could happen, but the reasoning is limited by dynamic analysis of some tests. We could actually change that. So right now, because of software security updates, et cetera, really every single piece of an interesting, important software is connected in a way where we could get high-level information about every single execution that has ever happened. And we could simply collect that from every single software user. So the proposal is then a data-driven software security model that uses historical evidence to guide enforcement. So we get the policy for free because we just look at what has happened in the past. And we somehow take some abstraction of what has happened in the past and say that's what's supposed to happen in the future. And we've solved the hardest problem in software security, which is figuring out what the policy is. And in the associated paper, I define this abstraction of an empirical program that captures at some level of abstraction all of the security relevant event ever seen in every single execution, including executions during test, including executions during trial deployments, et cetera. Now, in the model of security, this is very simple. This is the canonical authentication and authorization model of Lampson. It has sort of an outlet for audit records. Now you simply say that, well, that's not just an outlet, that's also an inlet. We have to look at what has happened to figure out what should be happening. And there's an alternative model of software security, a security model that's based on information flow, and it's exactly the same theory. We look at how has information flowed in the past to figure out how should information be allowed to flow in the future. Now, what would actually benefit here? Well, the Microsoft Windows Solitaire game could always be used as a complete network command and control server that captured everything that you were doing and controlled your computer in arbitrary ways. It has all of the networking functionality built in. It has all of the necessary libraries to control and command different processes, inject code, et cetera, et cetera. In fact, it has unbounded behavior. But it has never used, for any reasonable purpose, the networking libraries. So if you had information on what I'm sure are hundreds of billions of executions of the solitaire game, you would realize that networking is not something that it really does. And this historical evidence would allow you to prevent that process from being used as a host for a remote intrusion tool. Similarly, with the Heartbleed vulnerability in OpenSSL, if your abstraction of what the program has done in the past simply captures what functions or messages are invoked and what is the magnitude of their arguments. So one of the messages was a keep alive ping. You would know that OpenSSL actually doesn't do a lot of keep alives because that code was relatively recent. It wasn't frequently used on the internet. But some of them existed. What didn't exist was any keep alives with a large buffer. It's simply, or a huge buffer, let's say that. So you would actually be able to at least eliminate the magnitude of the exfiltration angle here. Now, possibly you could actually say that this is so infrequent that in critical deployments like at Google, we're simply not going to allow that feature. Nobody hardly uses it. This is a common thing that Google does. It takes specs and simply decides to implement a subspec to eliminate dusty corners, because in the dusty corners, the dragons lurk. So similarly, in the beginning of this year, there was a key cuddle system call that's in Linux. The key cuddle system call had a description of a key chain. It's actually a security measure in the Linux kernel added in 2.6 for keeping secrets in the kernel that processes can use, but you don't have to get the secrets out. Well, similarly to Heartbleed, there is a problem in one of the control structures. This allowed arbitrary takeover of the Linux kernel, ring 0 code running. Interestingly, this system call is never invoked by any software, except for the key cuddle utility. Now, it's potentially used by software. So in that Pentagon building, there is a key cuddle system call in some glibc library. It's just that nobody ever calls it in any reasonable software. So we have not made use of that historical evidence in most cases. I'll give you one example that counters that at the end. But we should, because that's a very dangerous system call. In fact, all system calls are dangerous, especially the uncommonly used with complex arguments like this one. Now, how would we actually apply data-driven software security? Well, we define what the program is. The program could be a Linux binary or source code or something like that. What's our security relevant event? Is it an RPC message with some abstraction of the arguments, or is it simply a system call? Some simple set is what we've been using at Google and what I'm proposing here. Not a trace abstraction or an n-gram or something more complex like that. By keeping it to simple sets of observed behavior, it's very easy to collect and merge sets of behavior from all instances of the software and interpret and enforce that. Enforcing, for instance, how system calls should be executed is relatively simple, especially in the latest versions of the Linux kernel, which include better mechanisms for that, some of which were actually developed and deployed to support this type of enforcement. Now, one easy thing to do is just simply focus on what is dynamically dead. So remember that Pentagon-sized building. Now, clearly, to make orange juice, most of that building is not going to be used. All of that building is a potential security risk. And in fact, that building includes code and behavior that allow bad guys to do arbitrary things. So if you think about Hello World in Java, take the Hello World program in Java, execute it with the Sun, or now Oracle, Java runtime, and try to reason statically about what might this Hello World program do. If you include the command line arguments to the Java runtime tool, you immediately have to say, well, this program could do arbitrary things, because I don't know the environment, and therefore I don't know the class loaders, I don't know the static initializers of the classes. In fact, this code can do arbitrary things. Most programs, when subjected to an analysis without knowing the precise execution environment, you find out that, yes, like a lamp stack, they can do pretty much arbitrary things and behave arbitrarily at their interface, which might be a system call interface or a network interface. That's not a good situation to be in, and historical evidence would allow us to greatly lock that down. In particular, we would be able to figure out what never happens, which is most things. Most things are not going to happen. Now, importantly, you have to capture all executions. It's not enough to just look at the things that happen commonly enough to be seen during some training examples. And you have to capture all of the different users and contexts, because those vary widely. If you try to deploy anything in real world, you'll see that users are very innovative and do weird things, and you have a long tail of behaviors. Now, if you capture all of the behaviors, you're left with the question that if something has not happened in millions or billions of executions, and is now happening for the very first time, even if that's a feature that's in your program, it's a command line argument, it's a module that is there and written by the developer. If nobody tested it, if nobody ever used it before, is that a feature or is that a bug? Is the use of this code for the very first time on some user's machine a bug or something that you want to allow? And it's easy to argue that, well, it's easier to treat it as a bug, file a bug report and say, you actually have to test this and ship it in the next version as something you want to support. Now, that gets into versioning and how you might actually deploy this in practice. Fortunately, most software is rolled out, most software is used at scale and affects a lot of users, is rolled out in this sort of crossing the chasm curve, where you have test-driven development or some reasonable process early on. You have trial deployments, say with Chrome, you have a dev release and a beta release, and then only eventually you have a gradual rollout of a stable release, all of which will give you plenty of time and data to build a reasonable profile of historical evidence to do enforcement when the code is affecting a lot of people. And you have to do that with every single release and sort of look at differences between releases. Now, that's the approach. What are the challenges? There's actually a bunch of challenges to doing this. First of all, let's look at how might we actually monitor things efficiently enough. If we're going to add monitoring code to every single execution of every single program, we better be doing that efficiently. If nothing else, we're going to be drinking the battery of people's mobile devices because everything is mobile now. So we actually have done work on this with a bunch of collaborators at Google. And we focused on the simple aspect of system call tracing. And so we put, as I said, some things into the Linux kernel, like alt-syscall is the latest one, that actually allow for very efficient monitoring of what system calls are made. In particular, it allows for especially efficient monitoring of what system calls are not made, because you only have to deal with the first time that something has happened, there's a one-time cost there, and so on. Interestingly, so this data is sort of an abstraction of a big binary, and when I say a big binary, I mean a binary that was so big we had to modify the linker, standard linker in Linux, because the debug build of the binary is more than 2 gigabytes. So this is a very big binary. The binary in the limit only uses about 80 system calls. Now, it's an internal binary at Google. What's even more interesting is that eventually this binary pretty much does a handful of system calls. There's a bunch of stuff that happens during sort of libc type startup, and then there is the sort of app startup that has most of the fancy system call work, but then eventually this is a relatively simple behavior profile. And similarly with the behavior on the network interfaces. So if you choose the wrong abstraction, however, and you choose the wrong mechanisms, like let's say you wanted to estimate detailed frequencies and build up frequencies of different system calls, you'd find that this is much harder. And this is just sort of an example of how much variance you could get with sort of doing monitoring at the wrong level and trying to count things. So here you see noise adding up as things become less frequent. So I'll get to you later, Sriram, questions at the end. So now I promised that the buzzwords in the title were not just there for show. So we actually implemented a bunch of mechanisms to try to make this approach realizable in practice. One of the things is, how can we learn from every user's machine without violating that user's privacy? And so my favorite example here is that at a certain point about 10 years ago, a certain function in the FFmpeg player relating to DivX codecs was basically one-to-one associated with playing stolen movies, copyrighted movies, and actually could get you easily into a lawsuit with some very litigious parties. Now, collecting detailed information on who is using that function would have been bad. Certainly, you wouldn't want a database of that. So we developed ways of collecting data about what's happening on client machines with privacy. This has recently been taken up by Apple and announced. So I'll give you some details. From what I can tell, what they're doing is indistinguishable from what I'll describe to you. So you have a picture here, and we'd like to learn this picture with privacy. If we look closely at what's happening on individual machines, we'd see detailed information. Turns out that we can add a lot of noise to that detailed information and zoom out and still see the big picture. So, and that noise can be added in such a way that it gives the strongest form of privacy that people know how to achieve, which is this differential privacy stuff. We used that in Chrome for the last couple of years. Here's, for instance, a chart that shows who on the web is still using Silverlight. It's a question that we wanted to know at a certain point because we wanted to try to get rid of Silverlight usage. So Rapport actually does things on the client side. That means that we can give rigorous and meaningful privacy guarantees for each user because they add noise to their own data before sending it, and they can reason about what their privacy leakage is without thinking about the rest of the world or without trusting anybody. There is no central database of actual user data that could be attacked or subpoenaed. And there are no externalities from like sending unique identifiers or something like that. So it works quite well for URLs and other types of things like that. This is statistics on home pages because people can set home pages as whatever string they want, like their own personal server. That's also privacy concerns. So here we can basically see the forest without possibility of seeing any one of the trees. It works as follows, just very quickly, because we're in Italy. I ask you, have you ever been a member of the National Fascist Party, which was Mussolini's party? And you might be embarrassed to say yes at certain points in history. And so instead of answering truthfully, we agree ahead of time that you will flip a coin, and if the coin comes up heads, you will say yes, the embarrassing answer. If the coin comes up tails, you will tell the truth. Now I know that half of you will say yes because of the coin, so I can just subtract out half of you as the yeses, and I can then see the ratio of the remaining answers, and that will be a very, very good estimate of how many people actually used to be members of the Nationalist Fascist Party. So now with the rise of sort of nationalistic parties again in Europe, the no answer might be sensitive as well. So it might be embarrassing to say, no, I've never been a member of the National Fascist Party. And so that's easy to do. That side of it is just, instead of deciding ahead of time that you will say yes if the coin comes up heads, we will say, okay, we'll flip another coin if the coin comes up heads, and you will just say yes or no based on that other coin. Turns out that this way of answering has differential privacy, which, as I said, is the best we can do. Now, effectively what this means is that instead of strings reported, we actually have a signal. Here are 4 signal bits, but this signal is actually masked with a tremendous amount of noise, so what gets sent is the bits at the bottom. And notice that some of the signal bits actually get canceled out. This is actually an open source project, has been up for a couple of years, and anybody can use this. Now, finally, and I know that I'm kind of out of time, deep learning, or the fancy machine learning that people are doing, is a hot topic in security and in many other fields. I'm not a big believer in its use for many traditional security purposes, like antivirus and so on. However, what it is good at is trying to figure out what do people really think. So that's sort of approximating what a person would do is something that deep learning is actually good at. And so if we look at how people relate to software, even software that's complex as a Pentagon-sized building, we might actually figure out that people expect that building to be creating orange juice for them. And that's, in fact, how they want that building to behave as an orange juice maker. So we can then take software that does one purpose, like orange juice making, and group that software and try to figure out what are the differences between all of the orange juice makers, and which ones are kind of like black sheep. They're doing things weirdly and more aggressively than the others. And we have done this. This is actually deployed in the Play Store at Google as a way of ranking what software does. And you can see that users expect, for instance, gaming and messaging apps to use the internet, but they're not so sure that messaging apps should be making phone calls, but absolutely not, gaming apps should not be making phone calls. And so therefore, a gaming app, so we can sort of actually use a deep learning model to learn this, and then use the user's assumption that the game is not going to be making phone calls to figure out who are the black sheeps amongst games. And so actually what we do is we take metadata, like the text and so on for the apps, we do a deep learning analysis on that, cluster it, and the clustering actually has this very nice property in deep learning where the positions of different points. This is called a deep learning embedding. In particular, we use something called word to vec. And the relationships here between different software and so on are such that not only are all of the messaging apps together, but if you take a messaging app and you go in the direction of a game, you will actually get a gamified messaging app. So that's where you will find things. Now, data-driven software security really means that we're trying to limit what can happen, do attack surface reduction, similar to firewalls, trying to make lamp stacks only make orange juice. So it's certainly worth considering. I said I promised that I would tell you something that actually has used this in practice. It turns out the machine I'm using here, Chrome OS, was developed using a technique similar to this, and a lot of the approaches I've been talking about were used to define a sandbox for everything that happens on this machine, partly as a response, as a result of that, actually directly as a result of that. The key cuddle attack at the beginning of the year had no impact on the Chromebooks. So with that, I can take questions. Sridham.
So you had that picture where you had the vertical bars, and I'm trying to understand, you had these very hard boundaries to which you attached an interpretation saying this was the initialization, this was the app startup. And I guess I'm trying to understand, first of all, how do you know when to draw, I mean, first of all, presumably the bars are completely a matter of interpretation that you superimposed, but there's kind of a learning that's happening that's learning something like the bar. Right, and so what does it mean to learn that bar, and is it over physical time or virtual time? How do you account for machine differences, synchronicity, things like that?
So
there's a lot of interpretation.
That's a complex question. There's a lot of interpretation. Here, as elsewhere, I would advocate that one start with something very, very simple. In this particular case, software at Google has a very well-defined library initialization time and software initialization time or application initialization time, and there's a barrier after the application has initialized before it starts production use. And this is a universal thing, certainly true for this particular binary. It is interesting that you can have different abstractions, like are events in the same thread treated differently than events in different threads, or do you actually, so you can define the abstraction in many different ways. Again, there I would start by something very simple. Let's look at the, and that's where having a set is very simple. We can just take the set of things that happen in all threads and merge them together, and that's the set of things that happen in this program and so on. But clearly, you could try to be more fine-grained.
So follow-up question then. Some years ago, we worked on something called participatory networking, which is where applications talk to the network and told them a little more about what the app is doing so they can get much better performance from network. So I'm seeing a connection here, and I'm wondering whether it makes sense to have a participatory operating system as well, where an application actually sends high-level signals down to the operating system or some lower-level monitoring layer, saying, this is a semantic position in my program, and that would give much richer information to the monitoring system. And it's pretty likely.
Absolutely, yes. And so we can, in fact, take two very important and popular points in that particular space. One of them is the permission model, which is now somewhat ubiquitous on Android and so on. The other one is the zygote model, which is used in Chrome, where you actually start off with a fully fledged process and have that process lower its privileges permanently and say that I am now done initializing. I only want to do those handful of lines afterwards. And this is something the application chooses to do. And but yes, absolutely true. Yes.
It's about enforcement. When you detect some anomaly, how do you, if you stop the application, sometimes that is too dramatic. I know you are not making peacemakers, but you can lose some mission critical information or.
Yeah. So the deployment scenario matters here. What the deployment scenario that I have been working with mostly is the deployment scenario at Google, where you have, let's say, 1 million users or 1 billion users. Why, add 3 zeros, fine. So each one of those users may be happier if you decide to shut down what is happening on their machine if there is a significant risk that it is a security violation, and then the user has to retry. So think about it as somebody is operating in the telephone center and they pull a wire and you have to redial. Redialing will give you the service you want. Maybe permanently you cannot go to this one web page because it always crashes, but the rest of the web seems to work. Now, again, if you have done your models correctly, this may be preferable than being completely open, which is the standard at the moment. In the back-end data center, we have something very similar where we have maybe hundreds of thousands of processes that are effectively doing the same thing, and the software is written in such a way that any one of them can go away at any point because they're not mission critical. They're actually designed to run in a failure environment, and so we can actually halt them. There is a point, however, that I didn't make very clearly in the talk because of time. You have to actually know and do statistical estimates of how likely is it that you have converged in your policies. And it turns out that you can do that. You can actually look at how much data have I learned so far in my tests and my dev and beta deployments, and estimate the likelihood that something will happen in the field. And when that likelihood has gone down low enough, you can actually enforce with high confidence that not very many users will be affected. In some cases, it's not going to converge. For instance, if you try to learn policies about what URLs people type into the URL bar, it simply won't converge. In other cases, like system calls, the set of system calls, it will converge, and you will get to that point.
As you are learning the models, you always will have some variation. So do you have data on actual false rate positives?
Yes, we have, as I said, so you basically converge until there is no false positive, and you can treat every single false positive as a bug. Okay. And so you can, in fact, automatically file a bug report for the false positive and so on. There is some possibility that there's a Y2K-like scenario where the software will, on every single instance, behave in a different way that has not been tested, but is still critical to work in some way. So in those cases, what we've decided is that after a certain amount of failures, we may actually keep a counter and simply fail open. So if 100,000 users have had a problem that is blocking them deterministically every single time they try to run their web browser, you may decide to let that happen. But that should give enough time for the security team or whatever team is handling those types of things to do at least a preliminary assessment. But in our experience, like for things like system call, those types of things don't happen. It's just that, you know, there's a theory that they might happen. There's an interesting connection here between PL theory and practice. Like maybe static analysis could help assess how likely things like that are to happen.
Okay, let's thank the speaker.